All right, welcome to the next session. My name's Andrea Boyd. I am Italian. I work at the European Space Agency and I formerly worked at BHP. I get asked often, what's the differences between mining and space? I mean, there are a lot of similarities. It's both really, high risk, low fault tolerance, really high emphasis on safety, particularly for humans and working with a lot of expensive equipment. The biggest difference for me, since I work on the space station now, is that I'm not the one in oranges that has to go out when the breakdown phone rings. I can relay to astronauts what they need to do. So let's talk today about astronaut exploration, analogues, and future lunar in-situ resource utilization. So currently our biggest exploration, there was an amazing moment in time where all of the different space agencies around the world were working on building their own new space station, and the engineers were able to get together and say, well, what if we made some standard international interfaces so that we could assemble them together in space and have one large international space station. And there was an amazing intergovernmental agreement that came into effect and is still functional today. It's completely above politics, regardless of what is happening on Earth. We work together really seamlessly to work with the International Space Station, and we've got humans continuously in space for 22 years this year in November. The space station itself, it's about the size of a soccer field altogether, and the habitable module, which comprises 4 international space research laboratories, is about the internal capacity of an international large passenger plane. There's not just Houston like the movies. We have 5 mission controls for the space station. So we do have Houston, of course, Huntsville also in the US. We have Moscow in Russia, Tsukuba in Japan, and Oberpfaffenhofen in Germany, which we abbreviate to Munich. The space station itself, internally in these 4 laboratories, we're running hundreds of different science experiments, from basic science to medical research to cutting-edge technology to benefit our lives back on Earth. There are many challenges as well as joys of living in space. One of the biggest ones that we have to do is the countermeasures for microgravity. Our bodies adapt really well when we go up into microgravity, but if we want to be able to come back down to Earth again, we've discovered around 2.5 hours of exercise per day between cardio and resistive exercise to bring all of the effects of microgravity, keep them below the clinical horizon and towards a 1G plateau so the astronauts can safely return. All of the amazing photos and videos that you see from the space station come from the cupola, which we also use for complex remote robotic operations and control for the astronauts. We do live stream from the space station cameras all the time, and we have embedded space-to-ground audio within that. Anytime you hear an Australian accent, it's me. The operations are really, really global, all the way west to east across the Earth between the engineering, the mission controls, and the operations centres for the space station. We work quite harmoniously together. The crews are extremely multinational as well, and they'll train together for about 2.5 years each, going around Houston, Cologne in Germany, Moscow in Russia, and Tsukuba in Japan for their mission. And you can see a recent photo of the crew, a combination of Russian, American, Italian, and Emirati astronauts there. When crew are not training for the space station, they can be selected for one of 2 analogues, either underwater or underground, or geological exploration missions. So similar to, before you were allowed on a mining site, particularly for working, of course, you need to certify in, the smelter, the refinery, for underground, whatever section that you're working in. Similarly, for the underground missions, the astronauts have to go through all the safety training, the certifications, and the examinations there. We have an extremely multinational crew when we go on these analogues, even more so than the space station. This one, for example, recently was a combination American, Russian, Japanese, European, and Chinese astronauts. They have to work autonomously in a lot of different environments, exploring underground, do geological surveys, mineral analysis, and get between some quite tight spaces in a few of the caverns as well, which we always joke is good practice for when they're on the space station. One of our storage modules is a bit of a spelunking expedition. We've expanded that since to further exploration. including going to some geologically significant areas that are really similar to the moon itself. And we have them work with professional geologists and metallurgists to be able to do visual analysis and sampling, and then different assay analysis as well within that in preparation for future lunar exploration. That is a photo of one of our crew abseiling down into the caves, and Jessica even brought up her caves shirt to the space station, and you can see where she's going over the Middle East just there. For the underwater missions, we have a permanent underwater base, which is on a deep sea reef base. It's fully pressurized at the same pressure as the water around it. Normally, if you dive to that depth, you can only stay for about 20-25 minutes before you need to resurface again. But because our crew live fully underwater, they are fully saturated, they're able to do exploration, extra vehicle activity, EVA, for up to 6 hours a day, as well as live and work and do research in the underwater laboratory. So we select a group of astronauts each year as well to do the underwater mission, and you can see them on EVA here. We set up a surface operations. You can see myself and my colleagues in the surface ops on the left. It's quite a small, tight-knit team. We all fit quite easily on a boat there. And for the EVA equipment, we do a combination of umbilicals together with backup air tanks. This is the most recent crew with Nemo 23. They were working on different lunar and regolith and resource utilization techniques, as well as practicing new operations and safety and different operations and technology demonstrations that we're going to use in future space and exploration missions. Some of the equipment that we use is quite similar to that on Apollo. You can see for the transport, which works really well underwater. We were also able on the EVAs to do research for future space exploration, as well as partner with some of the local marine specialists as well. And as one of the side projects, we were able to, over the years, regrow whole sections of coral reef. Coming back to my workplace, we do full-time training of astronauts with life-size space station modules and simulators, as well as we have the large neutral buoyancy facility where we can lower the space station modules in and then practice the EVA training as well as future lunar equipment. We also have a very futuristic division, which is looking at really advancing the technology readiness level of things that we're going to need for our lunar base and for lunar exploration. We have a lot of different experts and astronauts within this, as well as we generally have a group of around 50 students doing their master's or their PhD thesis. And that way they can work on things that are of interest to us, or if they propose an interesting enough idea, we'll take that on board and give them free rein to, try out different prototypes and see what works best. So we can really push the boundaries of technology for lunar mineral resources, and then the ones that work best, we'll bring them into our regular program. So for example, we have AI for everything from geological to ophthalmological analysis. We have a visual AI that can look at Apollo moon rocks and distinguish if they're, breccia versus basalt, for example. And then I'm currently also working on an AI for the space station where we are doing additional analysis of the astronauts' eyes because they have what's called space adaptation neurological syndrome. Because of fluid shifts, you have intracranial pressure, which affects the eyesight of the astronauts when they're in space, particularly in the males. So we have a lot of different ophthalmological analysis, and we have now an AI doing analysis as well as the ophthalmologist, and we're doing a comparison of that to be able to optimize the algorithms behind it. We have a lot of human-machine interface with our augmented reality programs. We've got virtual reality programs for training for different EVAs, and haptic and tactile force feedback programs as well within our robotics division. We started off with a very simple force feedback handshake with an astronaut on space and on Earth, and we've also augmented all the way up until doing an exoskeleton which can then control an end effector of a robot which is doing planetary surface explorations and is able to manipulate objects down to the millimeter through that interface. For the augmented reality, it's really useful to be able to be hands-free on the space station when you're doing operations that require a lot of detail, and then be able to see, the procedure, the next step, details about what you're working on without having to go back and check the procedure, and you're able to stay hands busy. Also for identifying what is in certain storage bags, for example. All of our storage bags are kind of identical looking white and blue bags. So being able to identify what is where is quite useful with that overlay. And we've also integrated into our medical program. So astronauts will come from different technical or military pilot backgrounds, and then they learn in basic training all the other types of engineering and science, together with medicine at quite a high level, and dentistry and many other skills that astronauts will need to have. So we've also integrated AR into our medical training program for crew. For the virtual reality, we've been using this for many years to train for spacewalks. So crew will first train in the virtual reality simulator to practice, and then they'll train in the large pool, of course, the NBL, and then they'll do the spacewalk in real life. And then we've also expanded that, so we're also doing now lunar EVA and lunar exploration training within the virtual reality environment. And then to bring that back to the analogues that we need for lunar exploration, we have built and are finalizing construction on a new lunar analog facility in Germany, and it's a 700-meter squared facility which has geologically accurate lunar regolith simulants. So this is exactly like the surface of the moon. We are only one of two places on Earth that has a certified lunar regolith simulant. We had geologists and metallurgists work together to find a source of rock that we were able to then process into a really accurate lunar surface in quite large quantities. This is also fully pressurized. It has a crane attached at the top, which we can attach to different equipment, as well as the EVA suits to do the gravity offset. It's only 1/6 of the Earth's gravity. And it's also got a pressurized habitation and research module attached to it. Now, this research module, much like when you're doing standalone operations in the remote desert for mineral exploration, it needs to be self-sufficient, and it needs to run purely on solar panel power, because that's what we're going to have on the moon. In particular, also for lunar operations, our battery system needs to be quite independent and efficient, because we have periods of up to 2 weeks of sunlight, but also up to 2 weeks of full darkness, where we need to be self-sufficient and run on stored energy. So we've set this up also for our simulation with Lunar as a completely autonomous energy facility that's off the grid. Inside, the whole facility is about 1,000 meters squared. As mentioned, most of it, 700 meters squared, is the surface, but the rest of it we have control rooms, and then so that we don't disturb operations, we also do have a public viewing area as well. We really want to, when we go back to the moon, have a much more sustainable presence to be able to use the things around us. We need to be able to practice with the gravity offset. We need to, figure out what we can do and how to utilize the lunar dust, as well as how to mitigate the problems that come with that. So beyond the International Space Station, we're looking at the Gateway, which is a cislunar orbit joint space station, and then we are going back to the moon to stay. The next mission is scheduled for 2024 with the Artemis program, and we're really looking forward to that exploration. There is nothing like it on Earth. We have a really amazing facility. As mentioned, we do have the gravity offset, and this is then going to be added to our suite of analog activities where the astronauts can be training for the space station, for the cislunar gateway, for the underground, for the underwater missions, for the exploration surface missions, and now in a fully integrated environment to be able to train also for our lunar missions with a really high emphasis on regolith utilization as well as gravity and microgravity countermeasures. When you do look at the moon, you look at the typical photos that you see coming from one of the rovers, for example, here, you can see it doesn't look like a lot at a first glance. You can see the tracks from the rover, you can see, basic rocks, a lot of moon dust, a few shadows, not too much else if you just take it at first glance. But when we look at it, when we're thinking of resource utilization, and particularly in situ resource utilization, which is important for the human presence to go back on the moon, I see, all right, I've got sunlight, I've got shadows, that means I've got solar power. I've got regolith, which we were also in some of our projects able to use successfully for energy storage as an alternative to batteries and as a complement to regular batteries. When we're at the poles, I can see also that we've got ice, an icy regolith, and from that we can get water. I see building materials from the regolith once we've processed it to do radiation protection for our habitats. I see the main component of regolith is actually oxygen. For us, that's both life support as well as fuel and propellant, and that saves us a lot when we're going to the moon. We don't have the luxury of running to the hardware store, or even if you're in a very remote mining or oil and gas site on Earth, you can still fly things in. We do not have that luxury on the moon. We have to work with what we've got in sight. So fortunately for us, the main component of regolith is actually oxygen, approximately 40%, as well as various other metallic and volatiles and useful resources. And then when we go further to the poles, additionally, it's icy regolith, and from that we're additionally able to extract water and some other volatiles and oxygen, and this is really, really important for us. So we've successfully done that in many prototypes, and the problem with doing that sort of extraction is we don't have gravity, as mentioned. We've only got 1/6 of gravity, and a lot of the typical techniques that we use in the mining industry, they're really reliant on water. It's no good for us because it evaporates. And we don't have gravity, which is also an essential part of a lot of techniques. So we really had to bring it back to basics and say, right, how can we do this and what can we work with? We did develop an ionic liquid, which we're able to do molten regolith electrolysis for extracting the oxygen, and that after that, we end up with a metallic alloy made of the other components you saw in the graph, which is actually, you can really clearly see that here, the pre and the post-processing, and you can see how metallic it looks after we've extracted all of the water and the oxygen from the regolith. And that's super useful because we've been able to use that as a feedstock for 3D printing. And the 3D printer, again, a lot of the 3D printers on Earth rely on a certain size particle feedstock as well as gravity to function. So we had to develop a new type of printer that's able to function in any rotation with or without gravity, as well as use a more recycled feedstock as well. It doesn't have to be pure, and we've experimented with the ratios because we really want to try and maximize the regolith ratio, and we're currently successfully printing at about 80% regolith. From that, we've also added it to things like PLA, and we have an experiment at the moment some of our students are working on with a photobioreactor, which is quite nice because it utilizes carbon dioxide from the astronauts, produces oxygen as a nice byproduct, and is able to integrate with that as well. So we have a lot of different prototypes, and regolith is really at the center of that because it's easy to get, you don't have any impacts, you can just scrape it off the surface, you've got an abundant supply, and this is the resource that we really want to capitalize on when we go back to the moon. We're able to use that for building materials, and we have a few different basic techniques. Microwave was actually one of our most successful techniques in doing like really high-powered, high-energy, strong heat microwaving for creating building materials, which we're able to use to coat the habitat as radiation protection. And then thermal sintering and laser is quite good as well. Focused sunlight hasn't been as great so far, but you know, we're working on different techniques and seeing how we can optimize that as well. The microwave protection, as mentioned, it's you know, from the regolith, we've been able to construct things all the way from very large structures, as you can see on the left, all the way down to, that's a 5-cent euro coin. And through, you know, laser sintering, we're also able to construct from the regolith very small things as well, you know, down to threaded screws, nuts, bolts, and further components that we're able to use and produce on demand for our future lunar base. We don't operate in a silo. There is actually a big international group, so the International Space Exploration Coordination Group. We meet quite regularly and we talk to each other about, you know, what we're working on in future space exploration programs. So we don't necessarily duplicate effort, and we're looking at a really global exploration to benefit humans. So we have a lot of really amazing projects, the low Earth orbit, the lunar ones, of course, Martian robotic ones. For human, it's really focused on the moon and lunar mineral resources. And going back to the astronauts, they have a lot of skills, as mentioned, including being taught photography and videography skills to be able to take amazing photos, like this one recently by my colleague Thomas Pesquet, who took a photo of the city that we're in currently, you know, 400 kilometers up, going by at 28,000 kilometers per hour. He was able to capture this wonderful image of Riyadh at night, and I would like to leave you with that as we enjoy the rest of the summit.